In the vast expanse of space, where celestial bodies dance to the rhythms of cosmic forces, the origin of our very own moon has been a subject of intrigue and wonder. How did this celestial companion that lights up our night sky come into existence? For years, astronomers have pieced together the story of a cataclysmic event that birthed the moon from the debris of a colossal collision between Earth and Mars-sized object known as Theia. Yet, pinning down the exact moment this event occurred has remained a challenge. Could the answers to this age-old question lie in a timeline that pushes the boundaries of our understanding to just 50 million years after the formation of the solar system? The theory that currently dominates our understanding of the moon's formation paints a picture of chaos and destruction on a cosmic scale. At the 55th Annual Lunar and Planetary Science Conference, LPSC 55, held in the Woodlands, Texas, researchers proposed a groundbreaking timeline that suggests the moon's genesis might have occurred much earlier than previously believed, around 50 million years following the birth of the solar system. This new timeline not only challenges our understanding of the moon's early days, but also attempts to reconcile conflicting evidence that has puzzled scientists for years. Dating the giant impact event has proven to be a complex puzzle, with different lines of evidence often painting contrasting pictures. One key piece of this puzzle comes from the orbits of planets and asteroids in our solar system. The instability in Jupiter's orbit, believed to be a significant factor in causing the cataclysmic impact, indicates that such an event would likely have occurred within the solar system's first 100 million years. This time frame is critical. Any later, and the orbital paths of the inner planets, including Earth, would have been drastically altered. Observation of Jupiter's Trojan asteroids, such as the binary pair Patroclus and Menoetius, which NASA's Lucy spacecraft aims to visit in 2033, supply the early timeline, suggesting the impact happened between 37 and 62 million years after the solar system formed. Yet, geological evidence seems to tell a different story. The earliest moon rocks formed from cooling magma date back to around 208 million years, while Earth's oldest crust formations appear around 218 million years. This stark discrepancy has led scientists to seek alternative methods to date the impact, including the decay of hafnium and tungsten, which suggests the moon's core might have formed around 50 million years after the solar system's creation. The intriguing proposal presented at LPSC 55 offers a comprehensive explanation that embraces all these conflicting pieces of evidence. It posits that after the initial collision and a subsequent 10 million year cooling period, the moon underwent a cycle of reheating caused by tidal forces from its unstable orbit around Earth that lasted until around the 200 million year mark. This theory explains the geological evidence by suggesting that the moon was not a static body after its formation, but went through significant thermal evolution, including reheating that could liquefy its surface again. Tidal forces resulting from the moon's shifting orbit and gravitational interactions with Earth could have induced this reheating, leading to the moon's surface melting and reforming. This phenomenon is not unique to the moon. We observe similar tidal forces at work on Jupiter's moons, where they create volcanoes on Io and maintain liquid oceans beneath Europa's icy crust. Moreover, the process of cooling could have been slowed by a series of violent secondary impacts, as debris from the initial collision continued to bombard the moon for millions of years. These impacts would not only delay the moon's cooling, but also contribute to its geological complexity. Adding to the robustness of their proposal, the research team, led by Stephen J. Desch of Arizona State University and A.P. Jackson of Towson University, introduced a new piece of evidence: the decay of rubidium into strontium. This method, akin to the hafnium-tungsten decay analysis, provided an independent estimate that further supports the timeline of an early giant impact around 50 million years after the solar system's formation. This groundbreaking research not only offers a plausible timeline for the moon's formation, but also sheds light on the dynamic processes that have shaped not just the moon, but the entire solar system. By understanding these early events, we gain insight into the forces that have molded our cosmic neighborhood into the complex and fascinating structure we observe today.